Welcome to Lecture 6 of the Compton Lecture Series. I'm going to do just a moment's introduction, as we do each time, resituating you in terms of the whole scope of these lectures. So you've arrived at this November 8th lecture, which the first half of which is going to be Doug MacAyeal, talking about glacial engineering. Doug arrived in UChicago in 1983, did I remember right? A year after he published an abstract that talked about the possibility of glacial engineering. So he's going to talk for about half the time, and then we'll have a bit of a back and forth, and then I'll talk about some direct air capture industrial experience I had, and then try and draw some lessons from it about what's the appropriate role for commercial technology in these areas. So, Doug, take it away.
Thank you, David. So I'm here not to talk about what forces climate to change, but what one of the most important responses to climate change is, and that is how the world's ice masses either grow in volume or shrink in volume, thereby causing sea level to change. And to give you a little bit of context, I show a graph that is the sea level history for the entire world. Obviously, sea level is a single benchmark, and it extends from 110,000 years in the past to the present. And what you're looking at is the top of the black line going down from the past to about 21,000 years ago. At 21,000 years ago, the sea level was 125 meters below where it is today. And human beings from about 70,000 years ago, our species, Homo sapiens, were able to walk from Africa, where we evolved, to all the other continents with the exception of Antarctica, via land bridges. And then between 21,000 years ago and the present, two things happened. One is the sea level rapidly rose as a result of natural climate change, the glacial interglacial cycle, which had nothing to do with what humans were doing, more to do with the way the Earth orbits, has little wobbles in it, and also natural regulation of CO2 in the past by natural processes. And what happened during that sea level rise is, first of all, the New World and the Old World got cut apart. You can no longer walk across the Bering Strait. So two civilizations evolved through time and only reconnected about 500 years ago. And then finally, sea level reached its current value about 8,000 years ago and has kind of been pegged there, plus or minus about 10 centimeters. And that is the time when all of civilization developed in our world of humanity. So this is the background, and what we need to do is ask, how is sea level likely to change in the future, and how will humans interact with that sea level change? Will they find it challenging, or will they find it to be an opportunity like those who were leaving Africa in the past? So I begin with a little primer on what the ice masses are on Earth. And there are three basic types of ice mass. The first is the kind that forms when you'd simply freeze either the ocean surface or the surface of Lake Michigan. We call this sea ice. It's very thin, typically lasts only a few years, and it serves an important role in nature. It's nature's solar radiation management scheme. Even though we know aerosols manage solar radiation, sea ice in the Arctic Ocean reflects a lot of sunlight, but sea ice is very vulnerable. It doesn't like to exist when the temperatures are significantly above freezing for a significant part of the year. But I'm not going to be talking about sea ice. The second of the three types of ice is snow, alpine snow and glaciers. And I show a beautiful Albert Bierstadt landscape painting here. This type of ice serves as nature's water delivery system. In South Asia and Southeast Asia, all the big rivers that are used for agriculture, like the Ganges and Brahmaputra and the Indus, get some of their water put into them from melting snow and ice, which usually takes a while, to get into the spring and summer. And this provides water to the agricultural system during the dry seasons. So this is a very vital form of ice, but it doesn't have much effect on sea level. If all the glaciers in the world were to melt, we'd have to walk back from the shoreline a little bit because it would be about 25 centimeters, maybe the height of this little screen here. The real player is the third element of ice mass, and this is what we call continental ice sheets. Yeah, the word ice sheet sounds funny. Why do we use sheets? It's because when you fly over Greenland or Antarctica, it looks like there's nothing but a flat surface of snow. But there is a shape to these things, which I'll be talking about in a minute. But these are nature's regulator of sea level. All of the sea level change that happened in the last 110,000 years ago that got humans out of Africa and into the New World across land bridges happened because ice sheets like Antarctica used to exist over Canada and Europe, and they melted away, allowing the sea level to rise to where it is today. But Antarctica and Greenland failed to melt at the end of the last glacial period for various reasons. And, we ask sometimes, are these glaciers sort of poised to continue to reduce their volume and make sea level go up or not? So that's a good question that we face as glaciologists. But the net amount of sea level tied up in Greenland and Antarctica today is 70 meters. If all of it were to melt, Memphis, Tennessee would be the new main seaport into the Gulf of America. Probably you could call it the Gulf of America because a lot of America would be gone, including Florida. So where is glacial ice likely to cause sea level change in the future? And again, I'm focusing on Antarctica and Greenland. We have these systems of observations that are satellites that go around the Earth and they ping with a laser beam down to the Earth's surface and measure the travel time in order to figure out where is the surface, what is the altitude of the surface. They call that laser altimetry. It's kind of like a boat sailing in Lake Michigan with a little sound wave telling you how deep the water is. You're figuring out where the bottom is. And what these satellites have done is they've looked at Antarctica and Greenland between 2011 and 2023 and asked where is the ice surface inflating, indicating that locally the volume of the ice is getting bigger, and where is it going down? A deflation of the surface, which means ice is going somewhere else. And where could ice go that's elsewhere but the ocean? And when you put water in the ocean has to incrementally go up. So what I show here is the color reddish, which says that over that 12-year period, the surface of this part of Antarctica in the Amundsen Sea has gone down by about 6 meters. And by the way, the average loss over this period of time is 142 gigatons of ice. And we think about gigatons when we talk about carbon. It turns out that 350 gigatons of ice is 1 centimeter of sea level rise. So we're not too scared right now about Antarctica, but what we're really scared about is if that red will suddenly increase its deflation rate, discharging more ice to the ocean. Greenland has the same story. It is showing change basically everywhere except at the very top. Needless to say, the center of Greenland is where the ice sheet is tallest, where you're at high altitude, so it hasn't quite gotten to a point where it melts there. But now we're losing ice into the ocean surrounding Greenland by simple melting during the summertime. So how does this work? And this is where I always have trouble explaining glaciology, because sometimes I myself don't understand it. So what I'm going to do is use an analogy or a metaphor or a physical model to help explain the concepts. I'm going to call it the water balloon model of continental ice sheets. And the idea of the water balloon is that, yes, it contains water, that if it spills out, it will seek its own level into the ocean and cause sea level to change. But a water balloon also has the rubber material that encloses it, which implies that there's a kind of stiffness. And the stiffness represents the hard, viscous elements of the ice that make the ice want to flow only very slowly rather than speedily like liquid water. So what happens when you take a water balloon like this and you put it on the Earth's surface like that, pretending that this table is the Earth's surface? The water balloon doesn't splash out on the surface, it remains perched. There's actually a distance going upward from the Earth's surface to the top of the water balloon. And that's the way it is for Antarctica and Greenland, although they would be kind of like flatter, pancakier like water balloons. And one of the things about ice when it gets to higher altitude, for example, in Antarctica, if you go up to the center of the Antarctic ice sheet, you'll be at 12 or 13,000 feet, whereas at the edge of Antarctica, you're at sea level. When you're at that high altitude, it gets colder. And we know that because all of us have probably encountered Hemingway's The Snows of Kilimanjaro. Kilimanjaro, of course, is the mountain that's 2 degrees from the Earth's equator. That's sort of like the last place you'd expect to see snow. But there is snow there on top of Kilimanjaro, including rapidly disappearing glaciers, because the altitude is above what we call the snowline elevation. Below the snowline, there's only rain, and any snow that gets there melts. Above the snowline, it's beautiful and white and crystalline, just as Hemingway implied. So here is a snowline drawn on a water balloon to represent the Greenlandic style of how climate impacts ice sheets. And what we see here is above the snowline, we have only accumulation of ice. Below the snowline, we only have ablation of ice. And usually these two areas are in balance, producing a steady state. But when climate changes, it warms the Earth, and what happens to the snowline? It goes up. So that means less of the ice sheet's surface is above the snowline and more is below, and that's what causes Greenland to lose its ice and contribute to sea level. Antarctica, on the other hand, is so cold that it has no snowline, except a little tiny, I've drawn a snowline out of blue here, it's probably hard to see, a little tiny part of Antarctica, which is where the knot of the water balloon is. Right at the coastline of Antarctica, the ice flow gets really gnarly and tangly. It's like a hairball. And what happens is that's where the ocean tries to melt the ice. And if the ocean can untie the hairball of flow complexity right at the coast, then it's like untying the knot on the water balloon. And the water rushes out, not as liquid water from Antarctica, but as unmelted icebergs. And it's throwing ice cubes into the bin to make the water level go up. The ice cubes floating does the job. So climate attacks the knot. Here is a movie of how the ocean attacks the edges of the Antarctic ice sheet, even though the top of the Antarctic ice sheet is not melting. And this is what I'm going to be focusing on for the engineering aspects of this presentation. This was in CNN on their website earlier this week. That's one of the things we glaciologists do. We kind of have a contest to see who can find the glacier that's melting the fastest. And this was the latest entry. So there's a lot of people that live within 3 meters of sea level today. And 3 meters of sea level is the kind of outside prediction that the Intergovernmental Panel on Climate Change of the UN predicts is being feasible for the coming century or two. And if sea level does go up because of ice discharge from Antarctica and Greenland, there's going to be a lot of stranded assets in coastal infrastructure. Plus, you're going to have to deal with the fact that wetlands are reduced, and we know what happens when that happens. You become vulnerable to storm surges from hurricanes, even if your city is not under sea level. So there's no doubt that humans will respond in a myriad of individually optimized adaptations at a plethora of locations. I use the word myriad and plethora kind of as big words to mean a lot. So humans will be doing everything all over the planet, every nation for themselves, because nobody's going to not respond to sea level rise. So there's another question, but what if there could be a cooperative response to sea level rise, where all or some of the most capable nations focus on an engineering project, not at every coastal location, but rather at one, maybe, or two or three spots where the ice is going into the ocean. Sort of like engineering the Mississippi River or something like that. It's a big deal, but is this possible? And I'm going to claim that there's two ways to do it for Antarctica, and I'm not going to go beyond that for time's sake. One is you protect the knot on the water balloon that the ocean is trying to attack with its localized melting in some manner. And the other technique is, why not just tie a second knot or a third knot into it just to tie it tighter? So I'm going to talk about these two things. So the ocean is attacking the underside of ice shelves in Antarctica. This is a cross-section of Antarctica. The bedrock is sort of this bowl-shaped black line. The ice is a pillow water balloon sitting on top. And at the very edges on either side are the knots, and you can see the reddish warm water coming in to attack those knots. And the idea that is floating around in my community is to put up barriers in the ocean that would protect those knot areas, the grounding area, the floating areas, from oceanic heat. And the idea is to use a kind of shower curtain thing that we would put out in the ocean. And it might look like what you see in the map of Antarctica. There's a little red area there, maybe 200 or 300 kilometers of curtain, not necessarily blocking the full water column in that area, might save us from 2 or 3 meters of sea level rise over 500 years. We don't know what would happen after 500 years, but we'll see. So that's the first engineering scheme. Second engineering scheme is tie another knot, or tie the knot tighter. And it turns out we humans are really good at pumping fluids out of the earth. For example, we've pumped a lot of oil out of the ground. And could we harness our knowledge on that to do something for glaciers? And it turns out that all the glaciers that are dangerous for sea level rise are dangerous because they slide on slippery, wet bedrock. Even though it's cold at the top of the ice sheet, because of the geothermal heat, the bottoms have reached the melting point. And that water down there is a lubricant. And if you remove that water, there's a case to be made that you would either literally stop the flow of the glacier for a few hundred years, buying time, or you would at least slow it down. So those are the two engineering techniques. And with great respect to my colleague David Keith, I want to bring up what is called the David Keith principle. And this is something that David brought to Chicago that we really didn't think about that much before. David says that if you're going to propose a geoengineering scheme, you have to see it in nature. Nature has to present it as plausible. And in the case of David, in his previous talk, he spoke about Mount Pinatubo injecting sulfur aerosols to the atmosphere, and there was a climate change, little one after that for a few years. And David wouldn't be studying sulfur aerosols if it were not for the fact that there was a natural example. So now I ask myself, are there natural examples of the curtains or the pumping? And I'm going to say yes. So the first one is in the Ross Sea, in this little narrow area of Antarctica. And that's a place where I used to study the world's largest iceberg named B-15. And for about a period of 3 years, by utter accident, and I had no idea that there was any relevance to geoengineering at the time, I'm now showing you an upside-down version of that same scene. South is north and north is south now. But what you see is that there is a assemblage of these giant icebergs, and what they do is they make a blockade over a portion of the Ross Sea coastline that is like the scale of what we would want to cool down, let's say in the Amundsen Sea of Antarctica. And the icebergs only partially block the water column, but you can see with the red dotted line, there's a whole bunch of icebergs sitting there. And they were sitting there because some of them got jammed up against seabed shoals. They had run aground, things like that, so the wind couldn't blow them off. And I'll point out a cool fact. There's an iceberg called B15A up there. That iceberg, if it were made of dry ice, it would contain the CO2 that humans emit in 5 years. So think of that iceberg as being significant in terms of its mass as well. So that's nature's lesson that passes the Keith test. The other lesson from nature comes from these ice streams that drain into the Ross ice shelf. You see in the white box there are these little pillow things, and in between the little pillows there are these flat sort of channels. Those are places where the ice is flowing thousands of meters a year as opposed to like 1 meter a year. And I have a close-up over here. And when I was a graduate student applying for jobs at University of Chicago, I was studying these ice streams, and one of the mysteries was that the ice stream in white, even though you could see all the crevasses and see its living character as you look down at it, it was absolutely dead. It had no velocity whatsoever. And the reason that happened is because the ice stream that's in the red line there carved its way, clawed its way deeper into Antarctica, getting more ice to flow into it. And it stole the subglacial water system that normally would flow down the white ice stream and it stole it to go into the red. So the white ice stream response was just to die. And we know some interesting things. Here is a picture of the Sistina Glacier in Alaska, and what I want you to notice are these black lines that run on the surface of the glacier, which have these weird, big curving mollusks and variations, such as in the larger picture. And these lines they're called medial moraines, and they're caused by the two glaciers that are at the very top of the picture. One glacier on the upper left has surged with more flow and has pushed the medial moraine out into a big bleb out in the middle of the ice stream, crowding out the other glacier. So the significance of these lines is that they tell us a history of the flow of these glaciers, even though if there were no humans measuring it. So in Antarctica, we look at these same medial moraines on the Ross ice shelf, and I don't expect you to interpret this yourself, but the answer to our interpretations is that the ice stream that was shut down by water piracy has been dead for 160 years, and that means that's a good time scale for keeping ice from being active. And it also told us it took 10 years to shut it down. So that means that maybe this would not be a geoengineering project that has to be continuous, but maybe could occur for 10 years. So can we engineer this? I'm almost done. The answer is yes for oil fields, I think. There is one of the glaciers in Antarctica, and I've put on top of it to scale maps of the Kuwait-Burgan oil production field, the subway system of New York City with all of its tunnels, and also the Three Gorges Dam and reservoir in China, the largest dam in the world. So certainly we have manipulated both surface and subterranean water at a scale that is comparable to the scale of these ice streams in Antarctica. And then what about the curtains, the shower curtain to protect the ocean, keep the ocean heat away, just like those icebergs did? And what I did is I found the literature for what are called an unglamorous but essential phase of naval warfare, which is what is called a submarine net. And it turns out humans have engineered curtains that cover significant parts of the ocean. The Straits of Dover, 15 miles wide, had a curtain of steel across it 200 meters deep, because that's the crush depth for submarines during World War I and basically World War II. And in the World War II time frame, the United States built tens of thousands of yards of anti-torpedo nets out of steel, and these would hang down about 50 to 100 meters. And they did it for $120 million between 1940 and 1945. So again, an engineering fact that happened then, perhaps that could be applied into the future. So at this point, I'm going to stop and just repeat the question that we try to think about here as glaciologists. Can a local glacier intervention or local engineering scheme limited to a single or a couple of places in Antarctica and Greenland slow or reduce global sea level that if impacts everyone on Earth? Is that a possibility? Thank you.
Stay up for a second. Thanks so much. Maybe I've got two questions for you, Doug. One is, let's suppose that you were in charge of a research program to make progress on this, and just to make it concrete, let's suppose that research program was $100 million a year, which may seem like a lot of money, but I'll give you some context. So the world is spending about $1 trillion a year on clean energy right now, and about $10 billion a year on all climate science globally, depending on how you define it. So $100 million a year would actually be a quite appropriately small flow of money from climate science, at least appropriate in my view. So let's say that there was going to build up to be that. What would be some of the big elements of how we'd actually use that kind of money to resolve some of these uncertainties?
I think the first element would be to deploy a cadre of researchers to really apply the David Keith principle and study all the natural examples of where glaciers have either stopped flowing or they've stopped making icebergs discharging into the ocean. And they should be studied to death. But that isn't a $100 million enterprise. That's more like $1.5 or $2 million over 5 years, for example. But if you want to have a big splash, then you have to try a field experiment at some scale. And Antarctica has the problem of the Antarctic Treaty, which forbids certain activities. I think my mic is going up and down, so I'll sort of shout. Greenland also has an indigenous population. So these two things are possibly preventing actual field experimentation. But to having said that, I would say set up a drilling program on a small glacier in Svalbard in the Arctic or in Axel Heiberg Island in Canada and see if you can stop the small glacier by pumping water out. And set up a curtain at a small fjord that has warm water coming into it and see what the problems are with the curtain. You know, does it fall apart in a storm? Do fish fail to move through it? You know, what are the impacts on the indigenous populations of people that live in Greenland? So that's my guess. Not a very ambitious one, but that's my first guess.
Thank you. And the next question would be just a few words on how you think about the kind of ethics and politics of this compared to some of the other geoengineering or climate intervention strategies.
First of all, it's important to realize that humans really do engineer the water systems of the Earth heavily all over the planet with their dams and rivers and things like that. And engineering a glacier is not too much of a step away. The advantage of engineering a glacier is that it provides a global social justice, because the change that you affect in reducing sea level through a single engineering project means that you've taken the pressure off not only the developed countries, but the underdeveloped countries who are much more likely to suffer from sea level changes because they don't have the ability to have a local response. So I view glacial geoengineering as being slightly more ethically understandable and a little bit easier than some of the other things that we face in this subject.
I agree. It's quite different. Thank you very much.
Thank
Thanks.
you.
Yeah, just to say one more word about situating these things. You may recall something I'm doing. Oh, it was on.
I know, and we're going to change.
Wiggly? Okay, got it. I'll take a second to wind up anyway. You may recall that at the beginning I talked about kind of 4 fundamental dimensions of climate change and thought a little bit about how they're different of climate solution. Beginning, I thought about 4 fundamental dimensions of climate solutions and talked a bit about how they're different. And the obvious question is, how does this fit in? And I think one interesting way to think about it is this adaptation or is it geoengineering? And I think it's more like geoengineering, but let me give you the reason why. So adaptation, as I defined at the beginning, are effectively local actions which have local costs and local risks and provide some local reduction in the harms from climate change for a given amount of physical climate change. And most of the sunlight reflection methods we talked about have this kind of global character where they have actually quite distributed global benefits and quite distributed global risks, but not much that's local. These ideas would have local risks and effects at the place where you did the geoengineering, where you, if you successfully did this in Antarctica, you'd have some big environmental impact from all that industry in Antarctica for sure, but then you'd have some global benefit of reduced sea level rise. And that way, I think it's kind of in between the two, but a little more like a global scale climate intervention. So now for something quite different. So I'm going to tell you something about carbon engineering, a company that I founded that I'm not involved with anymore. And it does something called direct air capture, which means a machine that directly extracts carbon dioxide from the atmosphere and makes a pure stream of carbon dioxide. And I'm not telling you about this because I think that direct air capture is necessarily more important than other kinds of carbon removal. I don't. I think it's one of the interesting ones. And I'm not telling you about this because I think that carbon engineering's technology is necessarily better than our competitors. I don't. I'm really impressed with some of our competitors. I'm telling you about it because it's something I know a whole lot about and I have experience about, and I can tell you a kind of detailed story to give you a sense of, in one place, of some real engineering details of how this might work. So I'm going to, for the next little while, really just show you kind of classic engineering slides that I haven't looked at for a while about carbon engineering. And then I'm going to step back in the last few minutes and try and draw some lessons from the experience of carbon engineering for what is the appropriate and inappropriate role of industry and for-profit companies in these climate engineering technologies, because I think there are appropriate roles and there are quite inappropriate roles, some which have been in the news recently. That was my little bit of foreshadowing. So first of all, you need to say a little bit about how I got started. I'd say sometime around the early part of this century, maybe 2002 or 3, at a place at Carnegie Mellon University, we had some big effort on integrated assessment of climate change, trying to look across all these things. And a colleague, Klaus Lackner, who had really done the first serious analysis of this thing we now call direct air capture. And Klaus really argued that it could be cheap and could be important. And Klaus is a really smart and wonderful human, and it was interesting that he was saying that. But frankly, we were pretty skeptical. But it was relevant, and we had to kind of understand, in the context of this set of choices that humans might have, what the cost might be, because it really makes a difference to the world if the cost was more like $50 a ton, where you could really do it at a giant scale, whereas if the cost is $500 a ton, it really doesn't matter that much. So we at Carnegie Mellon, in this kind of integrated assessment mode, began to think, what would it cost to do direct air capture? Is Klaus Lackner right with the claims he made about costs? So this started out, what led to this company, not out of a desire to found a company or really out of a desire for a particular technology, but really out of a technology assessment exercise. But if you set out to assess the cost of some technology that doesn't exist in the commercial market that you just can't buy, the only way, at least the only way I think you could do that credibly, is to, as much as possible, develop a system which conserves mass and energy and is a real engineered system as much as it can be, that as much as possible is built on things that you can buy in the commercial market now, because those are the only things for which you know the costs. The things that aren't available in the commercial market, so you just don't know what they cost. So when you build a cost of a new thing, you need to build it as much as possible, build it up out of components that you can purchase in the commercial market because you know their costs. So we started down the road, first purely in academic land, trying to say, if you wanted to do direct air capture, how could you build it up out of existing commercial components so we could do costing? So that's how it started. And then I eventually left Carnegie Mellon and went back to Canada, and I was able to get some money, partly from Bill Gates, but still just pure, but it gave me some freedom to have sort of $500,000 a year to work on this with some postdocs, and I was in a place that had a lot of chemical engineers. But at this point, they still weren't thinking that much about it as a company, really at all, actually. We were just thinking about it as a way to understand what the system might be, what it might look like. And from the very beginning, we built hardware. So in the upper right here, the upper left here, you can see the spray tower that we built in 2005 in the engineering high bay at UChicago. And at that point, we were really excited about the idea that the cheap way to remove CO2 with this, we'll get to how this works, but with a strong base, a liquid that's got sodium or potassium hydroxide in it, was to spray that through the air. And we had ideas that that could be really cheap, and so that was the very first spray tower we did. And the guy standing at the bottom there, Kenton Heidel, was a farm boy from Saskatchewan that I hired because I was pretty confident that he could use power tools without hurting himself, and I was worried that if we built this, we'd end up hurting ourselves. And he actually became employee one of carbon engineering, and in fact, I'm still working with him on some of the stuff that Cale might have mentioned about ocean alkalinity now. He's also now not in carbon engineering. So we started doing that from the very beginning, and we gradually built up, and all the way building hardware. And I think now I want to switch to telling you the core technology that we did. So I'll say this in a few bits. There's a lot of complexity here. I'm going to show you a bunch of slides with chemical engineering stuff and some nice pictures. But the big lesson of all of it is that all the big pieces of this technology were completely built on old things people have been doing for a long time. So the basic idea of the carbon engineering technology, which was completely an idea that Klaus Lackner had, wasn't our idea, was essentially this double chemical loop. Extracting from the complexity, what you have is on the left-hand side, let me get my pointer here, on the left-hand side, here, where you have this air contactor, you've got, and a contactor just means that you're bringing air in contact with some other fluid, and in chemical engineering terms, the CO2 is being transferred between the air and the other fluid. So the other fluid is a strong base. And that fits together with stuff you've already learned here, that CO2 is a weak acid, and acid and bases want to be together, and that's why if you have a strong base, it pulls CO2 out of the air. So we pull CO2 out of the air. The strong base we use is potassium hydroxide, and coming out of that, you have potassium carbonate, an aqueous solution, not a solid, an aqueous solution of potassium carbonate. And we'll talk more about how this air contactor works, but you can't just run that as your process. I mean, in principle, you can just go buy potassium hydroxide and then bury this stuff in the ground, but that would be a hopeless business because this stuff is really expensive and takes a lot of energy to make, so it doesn't work. So then what we have is a second reaction wheel where we're taking this potassium hydroxide into a big messy, hot bowl of bubbling chemical engineering stuff where we're mixing in calcium hydroxide, which you've again heard about in other contexts here. It's otherwise known as lime. So if you take limestone and you heat it up, you make lime. So we take this calcium hydroxide, mix it in here, and I think a good way to say this is CO2 likes to be with the calcium more than it likes to be with the potassium. So the CO2 grabs onto the calcium and makes calcium carbonate, which is the same chemical as limestone. So now we make calcium carbonate. Now we can take that calcium carbonate and heat it up and turn it back into lime, and then we've got this loop. We absolutely didn't think of that loop. You have all used the products of that loop a lot. That loop is basically exactly the same as the craft paper making process. I forget when the first patent was, but it's late 19th century, early 20th century. It is the way we make paper all over the world. So early in carbon engineering, we visited paper mills quite a lot. In a paper mill, you have exactly the same back end. This thing's almost the same, but you're not capturing CO2 from the air. What you're doing is pulling some carbon from the lignin that you're breaking up from the wood pulp, but you have the same two chemical loops. And so we're very much building on that kind of paper industry technology, which is immensely well worked out. So that gives you a kind of very top-level view of what this thing might look like. And now I'll give you a view that's still one level of complexity higher, and then I'll show you pictures of some pieces of it and tell you a bit about it. And then I'm going to try and step back. So this is a process flow diagram from a paper we published that kind of has all the flows of mass and energy in this system. And this already may look kind of complicated to you, but it's important to say this is ridiculously simplified compared to the real process flow diagram and the actual chemical engineering, actual plant that carbon engineering is now building in West Texas, which I'll show you later. So this is a very simplified kind of academic one. And there were lots of critics, we'll get to it in a second, who believed it wasn't even possible to capture CO2 out of the air without making more CO2 in the process than you could capture. And so we deliberately, in this particular academic paper that was useful to the company, we released all this information in a way that had only natural gas in, no electricity in. So it was natural gas in, CO2 in, and then that we were capturing the CO2 both from the natural gas and from the air. But I think it's important to say this is ridiculously simplified, even this one. So these complicated chemical engineering processes have tons of little wheels on top of wheels, and each of these things a chemical engineer would call a unit operation. And as much as possible, you're building them on top of other unit operations that people have hopefully done for half a century, so you have lots of suppliers and really know how they work. That's the kind of magic of doing big chemical engineering. So now I'll make it a bit simpler again, back to more or less something that looks a lot like that diagram 2 slides ago of the 2 wheels. This is going to tell you a little bit, and this is somewhat out of date. Be clear, carbon engineering sold, I'm not involved anymore. Oxy Petroleum owns it. They probably got different commercial relationships now, so it's an old slide, but it ties together with what was the industrial basis of the 3 big chunks. So the 3 big chunks here are the contactor, this pellet reactor, which I won't say that much about, and it gave us a lot of headaches, and the calciner. So the biggest and most important thing I'll talk about is that contactor, which is the hardest part of it, the most unusual part of it, capturing a huge amount of CO2. And to do that cheaply is the challenge. Maybe I didn't say that yet. It's crucial to say. There's nothing whatsoever technically interesting or difficult or challenging or academically cool about capturing CO2 from the air. It's been done for a very long time. There's no mystery. The hard part here is, can you do it at really large scale, millions or billions of tons a year at low cost with low footprint and low energy input? There were industrial applications of air capture for a long time, of capturing CO2 from the air. One of them was, it turns out, when you want to chill the air to get nitrogen out or get other argon out, you chill it, the CO2 that's in the air will freeze and gum up your machine. So in an air separation unit, which works by chilling the air and separating things, you need to scrub out that CO2 first so it doesn't bug you later on. And that was done for a long time just with a potassium or sodium hydroxide solution. So there's patents and commercial application of that going back to mid last century. And another application is in submarines. So submarines, and just one example, nuclear submarines, people are breathing out CO2 all the time. The CO2 would build up and choke people, and so you need to scrub the CO2 out of the air, and that's a commercial process that's used there and other places. So there's no big mystery about doing it. What we're trying to do is do it in this new way that's really cheap. And the big idea is we built this on top of industrial forced draft coolers. I'll show you pictures of those, but you've all seen them. They're all over the world. It's one of the most common pieces of industrial technology. And in a forced draft cooler, you bring water that's warm in contact with air, typically to cool the water, and you heat the air. There's also a reverse kind of thing for natural gas reheating that does the opposite. And then these calciners are used in a bunch of different technologies, including the back end of pulp and paper. So I'm going to first focus on that contactor. That's back to where we were, and just give you a sense of it. So that's the key thing, for reasons that I won't go into in detail, but if you just do the math, for every square meter of input of something you're going to scrub CO2 out of the air from, you're not going to get more than a few tons per year when you look at the realistic flows of air through it. If you turn up the fan higher, the fan energy kills you, so you kind of limit to speeds of a few meters a second, and that kind of drives this cost that when you do the math, you're getting a few tons per year, and when you do the math on how much you can afford to pay in capital cost per square meter of input, where you're then going to pay the bank for that capital cost because you're going to be borrowing the money, how much capital cost you can afford if you're going to keep costs overall under a couple $100 a ton, the answer is you can't afford to pay more than a few $1,000s of capital cost per square meter of input, and ideally you'd like it to be less than that. And so there's a bunch of really fancy ideas that people in academia have about how to capture CO2 from the air, involving metal organic frameworks and a bunch of stuff that gets published in high-end academic journals, all of which, from my perspective, is pretty irrelevant to doing this, because none of which is remotely cheap enough to be interesting. And also remember, if you're capturing CO2 from the air, the real air is not laboratory air. It's got pollutants in it, it rains, it's got bugs. You've got to have something that you can clean and maintain at low cost for a long time. And these big forced draft air contactors, you've all seen things a bit like this, have that property. They are pretty cheap, and we know how to operate them for 20 years. We know what their cost is, and we basically built on that technology. It's a little bit different, but it's the same basic idea, and that's the core thing, the foundation on which the carbon engineering idea was built on. The pellet reactor I'll say a little bit less about. It's proved maybe more problematic than we wished, but the idea was we wanted to get it's about the physical form. We wanted to have when you make that limestone, I said that you're basically adding lime and making limestone. The natural way you make it is in tiny little crystals that are like 10, 20 microns big. And those things are really hard to dewater. They make this slurry that's just really painful to work with. And wouldn't it be great if we could grow big crystals? It would be great. We don't know how. We can build big crystal aggregates, where big means about that big, a millimeter or two. And there's this pellet reactor technology that can do that. And so we've worked on that pellet reactor technology. That's this pellet reactor up here. I'll give you some pictures of what they look like. And the key thing again here is we didn't invent this. It was already used for large-scale water treatment and a bunch of technologies, including actually something to do with cheese making, where it's used for cleaning out the back end of the whey process. I actually don't understand that. And it's used for some other large-scale applications where we're doing that. It gives you some sense of what things look like now. This is all out of date, but this is in the carbon engineering facility when I was running it kind of almost 10 years ago. Things have got much bigger now, but that gives you a sense of our the very first time we tried to build a reasonable sized pellet reactor. And then finally, this calciner slaker. Again, calcining technology. These are taking high temperature and making limestone to lime. That technology goes back for thousands and thousands of years, in the sense that that's the foundation of how we make cement, and the Romans were making cement. But the issue is how to do that in a cost-effective way, and how to do it where you're capturing the CO2 that comes off. This is a bit like cement making, but when you get into the details, actually lime and cement look really very different. Cement has to be quite a lot higher temperature, sort of 1400-ish C, I forget, whereas for lime we just need to be at like 950 C, and there are a lot of reasons why it's quite different. You want to do it with CO2 capture, and there are a bunch of ways to do it, but the way that we focused on is doing natural gas combustion with oxygen, and then that makes you pure CO2 that then is easy to capture and compress. But there's a bunch of other ways to do it. So this gives you some look at just very high level at kind of some of the technology of what these things look like. This is a photo I took of the very first big oxy-fuel system being delivered to the carbon engineering site one morning in probably about, 2014 in Squamish, British Columbia, where carbon engineering had moved by that time. And these are some big industrial sites that are kind of similar. And then finally, this gives you a sense of what things look like recently. Or things look like kind of 6 or 8 years ago. So that gives you some very, very rough sense of it. But I'd say all the work here was detailed and kind of not intellectually, not academic exciting work. All the work was the details of actually making these individual process units work, figuring out how to integrate them in a way that was cheap, and figuring out how to make them do this new job. And now we're at a stage where a company called 1.5 and Oxy Petroleum are actually building a plant that is more than $1 billion in West Texas. This is a relatively recent video, so this is reality now. This is a plant that hopefully will be on late this year. This is the tower that has the lime calciner in it. These are the air contactors here, and these are the pellet reactor systems here, to give you some sense of it. So it's a giant site that would take about 500,000 tons of CO2 out of the air each year. So now I want to, and I should say, lots of issues and problems and lots of questions people have about selling to oil companies and so on, but I'm immensely excited that after all this time, and that's going to be lesson one, after 20 years, roughly, since we first really sketched that idea before it was a company, now, hopefully this year, we'll have an operating 500,000-ton-a-year plant, which will be by far bigger than any other direct air capture plant in the world. But still, 500,000 tons is in some sense pretty small, but it's at a big industrial scale. And now I want to step back and try and draw some lessons, good and bad, about these technologies from that experience. So the first lesson is it is profoundly hard to know the costs of some technology in advance. In my experience, and maybe you sense a bitterness, I have always been in universities. I love UChicago, and I've loved some other universities I've been at, but my experience of carbon engineering has made me in some ways profoundly skeptical of the limits of what academics know. So it's not hard, it turns out, to find academics who will offer opinions and publish papers that get peer-reviewed, that give you the price of various technologies that don't exist yet. And you can get academics to come together in groups run by the National Academy or the American Physical Society who will give opinions about what the costs of technologies that haven't yet entered the market are. I would say that if those people were actually able to do this with accuracy, if there was real information content in it, that industry and investors would be paying them a lot of money for those predictions. But they don't. And the reason is those predictions don't hold much value. It's just extremely hard to know what something costs without actually doing the work. So now I know probably as much as almost anybody about this, in the sense that I know about carbon engineering. There's a bunch of stuff I can share and some I can't, but also I'm actually quite friendly with the young people who founded Climeworks, our biggest competitor, and we've shared lots over the years, and I'm friendly with some of the other companies, so I know a fair amount. And my error bar for what it actually would cost to do this is still very large. It's just very hard to do. There was a point, maybe 6 or 8 years ago, where carbon engineering had probably spent more than $100 million actually doing all this engineering. And the uncertainties about costs were still factors of 2 or 3. These are very hard things to know. And I think it's tempting to think that you can go to the Intergovernmental Panel on Climate Change, which refers to various peer-reviewed literature, and that you can just sort of know what things cost and know the relative costs of things. And these costs matter because they matter for decisions about what we would do. But I think my big lesson is that it's very hard to know, and that academics are often not very helpful in that. They're extremely helpful in knowing the physics and the engineering and the chemistry and understanding how those fit together. That's fantastic. But costing is a different art with different expertise, and the people who are really good at it are often people in individual niches, either in consulting companies or at the top of big companies who really know what these things cost, and those people will not give that information out casually or for free. And for a thing that's never been built, nobody really knows the cost. So that's really my biggest lesson. It's very, very hard to know. I guess one way to think about it is cost has sort of 2 components. One is you need to be able to predict the performance. So if you build some physical thing, you need to be able to predict its performance. How much energy will it actually use? How much maintenance will it actually take in terms of money? How much, what will its environmental impacts be? What will its emissions be? Those are all performance predictions, and those are uncertain. And then the second thing is you've got to know what is the cost to build it at scale. And for complicated things like this that aren't easily moved, that are built in place, that cost itself varies with sort of construction cost indexes that vary around the world depending on cost of labor, moving stuff there, land, and those things vary cyclically, so knowing the cost at one time doesn't necessarily cost it something else, cost at some other time. I'll maybe just say another few words about that. I kind of hinted at it. I think, but I want to kind of burrow down to give you one example that really gives you a sense of the disconnect between the way academics think of things, where in academia, truth is that it's in a peer-reviewed paper. And in the business world that I've been in, truth is when you can buy it from a big vendor with a performance guarantee, you know the price. And those truths really don't talk to each other much. There was a moment where the American Physical Society, including people who, some of whom are my mentor, one particular one, Rob Sokolow, was my mentor, who I really just genuinely love, was running an effort to estimate the cost of air capture. I get why they want to do it. It's a legitimate, important question. We want to estimate the cost because it's important to public policy. This was around 2010 or so, and they were basically very dismissive, and it could have killed our company, so we were obviously pretty unhappy and upset with them. But there were cases where you could see this giant disconnect. So we were asserting things about how our contact were to work and how, particularly the so-called packing inside it, some corrugated plastic inside the packing, how it would work. And their view was, you haven't published. And our view was, it's unpublishable in a journal because what we're doing is basically boring 1950 stuff that no journal would want to publish because it's been done for 50 years. And we don't need to publish because we can go to the manufacturer of the packing, Brentwood Industries, and they have spec sheets and they deliver this in kind of $100 million quantities and they know what they're doing. And those two different views just didn't connect. And so in the end, the APS didn't accept our views about the way the packing would be built. And I think in hindsight on that topic, they were wrong, although on other topics, actually, they were right. It's a complicated story. But I think the big lesson is that it's very hard to know cost in advance. So what can we say about that? Stepping back, forgetting about direct air capture to all of carbon removal. As I've said a little bit earlier, my view is that it doesn't make sense to be doing carbon removal at giant scale in the next few decades. But there is a real case that humans might want to do carbon removal at giant scale in the latter half of the century. But that learning this stuff is slow. Remember my lesson 1 about it taking 20 years to get here. And just throwing money at academics to study the problem or admire the problem will not teach us that much. So if we really want to be able to have good knowledge in, say, 2045 about what large-scale carbon removal technologies might really cost, what their environmental impacts might be, we need to actually try a bunch of them at a scale that's big enough to assess those things. And that's still a scale, I think, that's much smaller than doing it. It's not gigatons a year, it's megatons a year in most cases, depends on the technology. But we need to do that. And then one other thing before it's a crucial lesson, I think we need to separate the assessment about the environmental impacts and kind of larger environmental performance, where I think academia and academia and governments and NGOs are exactly the right place. We need to separate that from the industrial piece of trying to do things cheaper. Just to say the obvious, once you have a company in industry, it wants to sell. It's always going to exaggerate how well it works. It's going to downplay the environmental impacts. That's just baked into the fact that you're trying to sell. And so the lesson there is we need to separate the two components. I think that's especially true in open ocean alkalinity, where one question is, if we distribute alkalinity, that would be the same actually lime or magnesium hydroxides, if we distribute it in the ocean a certain way, it's a question for geochemists and oceanographers what the environmental impacts would be. We need to do experiments. It's a question how effectively it would take CO2 to the air, and you heard a bit from MacAyeal. There's a bunch of us here working on it. We're very excited about it. And I absolutely, on those questions, trust academics much, much more than I would trust industry, which will always try and over-promote. But on the other hand, if you want to know what it would actually cost to deliver finely powdered calcium hydroxide to the ocean in a certain way in giant bulk carriers with billions of tons a year, you've got to have industry involved in a central way actually figuring out how to do it, because you just can't look that up from papers. And so to me, the key message is we've got to divide those two sides of it. For direct air capture, I think it was easy in a sense, because for direct air capture, because it's a kind of encapsulated system, you don't need to trust what Carbon Engineering or one of the other companies says, because in the end, if you build a direct air capture thing, it's trivially easy to measure the flow of CO2 down the hole. You can do that to 1% or better, and to measure emissions. And so some third-party government or consulting agency can easily make those calculations correctly. You don't have to depend on the trust of the company. But for other things, you do. And let me end with this crucial place. Some of you may have seen news in the last week or so. A lot of us inside knew this news was coming for the last year, but it broke about a week ago that there was an Israeli-American firm called Stardust that had raised $60 million to do sunlight reflection for the whole world in a commercial way, using some technology that they say is going to be safe and perfect in all sorts of amazing ways. And to be clear, the actual people running this company I've talked to, I think they are really thoughtful, earnest, serious, really smart engineers. But I strongly disagree with what they're doing, and I think it may be destructive to the broader field of sunlight reflection. Since that article, we found out that they've been pretty actively hiring a top lobbying firm to lobby Congress, and this is the way the kind of industrial world works. It has to work, and to be clear, of course, carbon dioxide sharing was lobbying Congress, but the big difference is with something like direct air capture, there's no mystery from the outside about how well it works. There's big questions about what it costs, but once you build one, third parties can easily validate how well it works. That is not true for sunlight reflection. So to me, there's a big difference here, and you might be interested in an article that myself and Danielle Visioni wrote, an op-ed that came out earlier this week that tried to really give a careful set of reasons why we think that what Stardust is doing is both unlikely to work out the way they say and unlikely to build trust. And the way I would say it is that for sunlight reflection, as we sort of hinted at, it's already cheap. The big thing is not making it cheaper, it's figuring out how effective it will be and what the environmental impacts are. And that's something that I think industry is spectacularly unsuited to do. That's the one thing industry doesn't really manufacture, is that kind of trust. So I want to distinguish the two. If you want to make cheap batteries or cheap solar panels, we absolutely need crazy, hard, competitive capitalism to make those things cheap. But again, we don't need to trust everything the battery company or the solar panel company does, because it's easy to, when they give us the product, it's easy to test them, and there are third-party companies that do the testing. So what we care about is just figuring out how to manufacture them cheaper. I don't think we could possibly do that by kind of government-controlled entities. I think that's where capital competition really has worked well, and that's what's brought us cheap batteries and cheap solar. Of course, not to say there's academic research didn't help. There's some wonderful academics working on batteries here, but that has been that case is where I'm not saying it clearly, but that's the case where that kind of industrial competition is doing the right thing. But for sunlight reflection, we don't need innovation to make it cheaper. It's already cheap. What we need is really understanding how it works, and that's where it seems to me for-profit action is uniquely unsuited. So I've kind of sketched what I think are kind of two extremes. To me, direct air capture, not saying anything special about our company, but direct air capture is on an extreme that's pretty close to like batteries and solar panels, where it's easy for third parties to check, so you can just kind of have competition to figure out how to do it. And sunlight reflection is kind of the other extreme, where it's extremely hard to check exactly how it's working, and you don't really need to make it cheaper. And then a bunch of the other technologies we've talked about here, open ocean alkalinity and adding enhanced rock weathering, are somewhere in the middle between them, and we need rules that are somewhere in the middle between them. So, thanks very much. Happy to take some questions for both of us.